All right. Hello, students. Welcome to your Unit 8 pre-lecture. We're just going to do a little bit of review on acid and base introduced in Unit 4. And then I'm also going to add some additional information as we look into really digging into acid-base calculations and, of course, particulate level understanding. So, quick reminder, according to the Bronsted-Lowry definition of an acid is a substance or species. I'm just going to say right now a species that, donates a H plus, which is equivalent to an H3O plus hydronium ion. Okay. Oftentimes water is the carrier for acid-base reactions. And that's why we see for this is like having an H plus and an H2O combined because water is often the carrier or the solution that we're in to perform acid base. And then I'll give this a name, hydronium ion. A little new term is that we can actually categorize an acid as a polyprotic or a monoprotic acid. So polyprotic acids, poly means many, protic proton. It's a acid that has two or more H plus to donate. So for an example, H2SO4 would be an example. It could donate one H and then it could donate in a second round the second H. Okay. So otherwise, we say that the opposite of this would be monoprotic, would be only one H proton available. Okay, so the Bronsted-Lowry base understanding, of course, is a species that accepts a proton. Okay, and then we often say that we can identify a base, specifically strong bases. I'm going to put this. Strong bases often have OH minus ion. And why does this make sense? Because an OH minus can accept an H plus and go to water. So that's kind of why we have this secondary understanding of an easy way to identify strong bases in particular, or they have an OH hydroxide ion, which is the part of that species, that functional group within a chemical species that can accept that proton. Okay, so quick note before I get into the next discussion on strong acids and bases versus weak acid and bases is that as I talk, realize that, or keep in mind that concentration does not always equal strength of the acid and base. So the concentration of acid or base is not necessarily an indicator of the strength. It just means I have more of a weak acid or more of a weak base, right? It doesn't mean I have a ton of weak and therefore I am necessarily a inherently strong acid. The strength of an acid or a base is inherent to its structure, not its amount. Okay. So that being said, what is a strong acid or base? Well, a strong acid or base is a acid or base that completely ionizes. Okay, so what does that mean? It means it will 100% of the time lose 100% of its H plus, or it will 100% of the time accept, 100% of the H pluses. And so that means some characteristics. It has strong electrical conductivity. And we also see that we can usually identify if it's a strong acid or weak base structurally by looking and recognizing that it has a weaker bond between the body of the compound and the actual ion itself. This is a little organic chem method. Oftentimes when we write R something, R and then some structure, what we say is that this is the rest of the molecule. And this is the important structural group that we focus on. So this is just kind of a little organic chem notation for you, for those of you that are looking into it. So what I say is that when there's a weaker bond between the molecule and the ion that molecule carries is actually pertinent to our discussion. So that would be the H plus or the OH, okay? So, and we're gonna get into that, by the way, in a little bit in class. This is gonna, oh, not that one, sorry. This whole look into how the structure affects the strength will be discussed in class. So we also know characteristic wise of a strong acid, strong base is that they produce weak conjugate acids / bases. So remember, a conjugate is the base of that species plus or minus a proton, okay? So you can guess then for weak acid, weak bases, we have basically everything flipped. A weak acid or a weak base, what we say is that it partially ionizes. That means it sometimes loses its ion or it sometimes accepts. Hint, hint, this means that we are in equilibrium. So weak acid and weak bases are actually an equilibrium reaction, but we'll get into that very soon. So then what are some of its characteristics? Well, low electrical conductivity because it just doesn't produce ions at the same rate. And then what we see is that the structural feature is that we actually see a stronger bond between the base structure of the acid or base and the relative ion that is being lost. Okay. And in this case, when I say lost for a base, it would be if it was an OH minus. Okay. And again, I direct you to my little comment above where this is totally an organic chemistry notation, where R just means the rest of the molecule. Okay. And then we see that they tend to produce strong conjugate acids / bases. So the conjugates end up being a better acid or a base. So we have some common weak acids that we can categorize based off of structure. And again, I will highlight that this discussion on how structure affects function or how structure affects properties of acid and bases, we will be addressing in class. Okay, and this kind of goes with it. But quickly, I'll just let you know that a really common weak acid is what we call a carboxylic group, carboxylic species, where again, organic chem notation, you have some group and it has a COOH, which looks like this. We would say it's a weak acid because according to weak acid, it has a really strong bond between the rest of the group and the pertinent structure. So there's an overall really, really strong bond between this carbon, O and OOH, and this H. We see a really strong, I guess you could say, attraction between these molecules, okay, and the H group. So that's just kind of how we would interpret this. And that means that, FYI, if you're putting it together, that means that the conjugate of an carboxylic species would be COO minus, and this would be a weak base. Okay. Oh, sorry, a strong base. A strong base because we have a weak acid and they tend to produce strong conjugates. So it would produce a strong conjugate base. Strong, let me put that in. Conjugate base. Okay, so just kind of trying to connect all these things together for you. Another common weak base species is, or I shouldn't say another, a common weak base species is what we call a nitrogenous species, English. And this is a nitrogen containing species. Okay, the big emphasis here obviously being nitrogen, right? And we also see and carboxylates. And carboxylates sound very familiar. These are, okay, a structure that looks like this. Oh my goodness. So what we see is, and now this is a carboxylate that comes, I feel like I actually miswrote that structure group because that looks far too familiar to our strong conjugate base. Okay, so no, it still works. It still works. So when I said that the conjugate base above, which has the same structure as a weak base below, I really should probably put stronger conjugate base so that it's a better base than it was as an acid is probably what I should put. I think that will help clarify. And then, but alone, when it starts off as a base, we would actually consider it more along the weak end. And so, yeah, this is a carboxylate, R dash structural group of RCOO minus. And what would that look like as a Lewis structure? It would look something like this. Okay, and then, and notice I'm not putting in the terminal and lone pairs and stuff right now because it's not important. And then for a nitrogenous species, that would be like a good example of a weak acid, weak base. We can kind of think of, trying to think, well, NH3, trying to think of a good example. Yeah, I think NH3 would be the best. So NH3, right? So that would be saying that for weak bases, we see that they have a stronger bond between the R and the ion. So what we see is that there's a pretty strong bond between this N and this H, or really any H. And so it's not really going to, well, first of all, if it accepts an H, okay, it doesn't, for a bit from the base point of view, it doesn't really want another H because that pushes it into an ion, a charged state, right? If you added an H plus, now you have NH4 plus, and that actually from the NH3 standpoint isn't as stable. Carrying a charge isn't as stable as being an uncharged species. So for NH3 base, weak base, it's not as stable to have a charge. And then I'll put a little note here above that better base than acid for kind of clarifying why the common weak acid carboxylic species example produces what we call a stronger conjugate base. But then we use that conjugate base as an example in the next section on common weak bases. It's because when I say a strong or a stronger conjugate base, it means it's better it produces a base that's a better base than the acid was as an acid. And then for common weak bases, when the carboxylate, the charged R rest of the molecule, COO minus carrying structure, okay? We consider it in the beginning, if it starts off as the beginning species, we consider it an actual weak base overall. So, sorry, I realize that's a little confusing, but you'll kind of get it the more you work with it. And yeah, So here's a table of a bunch of acids and their relative scale of acidity and basicity. I wouldn't feel the need to memorize this, but I would say this. As you look at this table, take note about what's at the extremes. What's an extremely strong acid? Okay, what's a really, really strong acid? Full, more complete ionization. And what's a really, really, really strong base? Okay, down here, right? Oof. Oh, strong base. And then what you also should think about is don't forget to pay attention during problems. That was not what I wanted. Pay attention when doing practice problems. Because they can teach you weak versus strong examples. So that's kind of how I would learn this table is I'd focus on memorizing maybe the weak and the very strong acid and the really strong base, and then let practice problems teach you. Like if you're looking at a practice problem and they keep on using NH3 as an example of a weak base, maybe you should just take note of that, right? So I would say your practice problem exposure will help you identify and get a feel for a lot of this table without strictly having to memorize it. Okay, so a quick note about the strong versus weak reactions, and I mentioned this above, is that when you look at strong acid-base reactions, for strong acid and strong base reactions, we see that it is irreversible. And we get a single arrow. But as I mentioned before, for weak acid / weak base reactions, we actually see a reversible process because it is only partially ionizing. So we get an equilibrium. And this equilibrium right here is going to have a K value that represents it, right? So Ka and Kb coming soon. All right. Equilibrium means that we are going to be tapping into unit 7 equilibrium. Okay, very soon. Hopefully you guys remember neutralization. That neutralization, right, is the process, right? It's the chemical process of an acid and a base, okay, exchanging H plus so that the moles of acid stoichiometrically equal or equivalent to the moles of base. Okay, so that's kind of unit 4 briefed over. We talked about a lot in unit 4. I don't feel the need to go super in depth, and you're going to be working a lot with it anyway in future practice problems. So just so you know, there's a specific type of acid-base subcategory other than just neutralization reactions, and that is known as hydrolysis. And that literally is just a fancy way of saying when you have an acid or base react with water as the other species. So instead of water being just the carrier here, where like the actual reaction occurs, now we're treating water as an actual reactant itself. And remember, water is amphiprodic, so that means it can act as either an acid or a base compared to the relative strength of the other species that you're reacting with. So hydrolysis is just a fancy term where we, instead of treating water just as the conditions that we're in, it's actually part of the reaction itself because it is the species that is reacting with the acid or base or doing that exchange. So that's just kind of like a little subtopic. You might hear the word hydrolysis in prompts. It's just a subcategory of neutralization reaction. And then, of course, when you do go through the process of neutralizing or exchanging a proton between an acid and a base, we, of course, get conjugate acid in pairs. Please do not forget how to label your conjugate acid pairs. These are species that differ by a proton from reactant to product side, right? So go ahead and take a moment to identify the following conjugate acid-base pairs and fill in the following table. And when you resume it, you should see the answers for him. Okay, so hopefully you got the following. Don't forget, there's a reason that we do say proton, right? We treat the H plus like a proton because it's like we're adding or subtracting a charge. So don't forget to reflect that and don't just exchange the proton and leave it at that. Remember that it carries a charge essentially. So you're also adding or subtracting charge to your conjugate species. So make sure your charges reflect that when you do write conjugate. Okay. Another little short review is on, I've already introduced this, measuring the potential of hydrogen or the potential of a hydroxide ion. pH is with respect to the acidic perspective, POH is with respect to the basic perspective, and we use a pH scale that goes from 1 to 14 to measure the relative acidity or basicity of an acid or a base sample. So this is a measure of relative acidity / basicity. I don't know how to spell basicity. Basicity of a sample. Of course, pH 7 is a very special value. pH 7 is what we consider neutral. And it is the pH of water, which I will discuss again in a second. Quick note about the logarithmic calculations for acid, base, pOH, and pH scale is that regarding the calculations for sig figs, we say that the decimals, the number of decimals is the counter of the sig fig, not the actual number in front. So for example, what I mean is that if you got a value of like 3.28 for your pH, okay, and I'll write this in black. If I got a value of pH equals 3.28, my sig figs are just 2 sig figs. I go off of the numbers past the decimal, after the decimal, as my sig fig calculations. It's kind of just to account for the logarithmic as an exact number because it's technically just a reflection of a power of 10. So anyway, it's just, or base, yeah, like log base 10 or whatever. So yeah, I here have a quick little summary of kind of manipulations you can do and the calculator. Don't forget this very important relationship right here that we can actually relate pH and pOH to 14. And that can help us if we were given like the base perspective. It can help us figure out the acidic value pH, or if we're giving the acidic perspective and pH and we wanted to know its pOH, we can do that without actually having to measure anything through this simple relationship. And then this is like the manipulation in the red, to the right of it. So go ahead and take a moment to convert pH to H3O plus hydronium ion concentration and reflect the number of sig figs. So go ahead and pause me and do that. All right, so hopefully you got the following values and you were able to identify how to count sig figs appropriately. When we talk about concentration of the hydronium ion or the hydroxide, if you were to flip perspective, it's standard sig fig rules, but when you look at the pH value, you only look at the numbers behind the decimal. So quick note, there are a couple instruments that we tend to use when measuring pH and in lab, at least when you're actually doing the experiment, and that is pH slips. Where you like dip it in, and it's all based on color. It's not very precise. but it gives you a general idea of what your sample would be in the range of. And then the most precise is digital pH electrodes. And I feel like some of you guys, if you've taken APES, you probably have worked with this. So measuring the conditions of your sample, and digital pH electrodes are the most precise instruments, at least accessible to high school students. So yeah. So I have a couple sample problems for you where you're going to use the relationship up here. Let me kind of walk you through, but actually, you know what I realized? Before we can do this one, I actually need to teach you one more thing, and that is the uniqueness of water. So don't forget that water is amphiprodic, which means it can donate or accept an H plus. It can act as an acid or a base. Some other examples would be many polyprotic acids are also considered amphiprotic because when it creates its conjugate could then reversible. If they went the other way, it could accept and act as a base. Okay, so look at the example above. So yeah, so water can either be an acid where it donates, okay, and becomes a hydronium ion, or water could act as a base and it could accept. And many polyprotic acids have a similar phenomena where its conjugate now can act as either an acid or a base because it has the ability to accept one more or give away one more. So I should actually emphasize that this is many polyprotic acids conjugates, many conjugate forms of polyprotic acids. Are considered amphiprotic. Okay, so and I'll even highlight it here, conjugate, and it is this conjugate right here that we see. Okay, so and then I'll quickly label this as this is the obviously water acting as an acid, and this is water acting as a base. Okay, so we know that water auto-ionizes, and that means that water, what does that mean? Auto-ionizes? Okay, that means that water will ionize itself in the self-transfer of H plus proton. And what we see then, we also could say it auto-neutralizes itself, or it neutralizes itself, which is why we say that water's pH is always 7. Because for every water neutralization, you get an OH minus ion and an H3O hydronium ion in a 1-to-1 ratio. Therefore, they stoichiometrically, the moles of acid equal the moles of base. So it just cancels itself out. Right? So this should be all sounding pretty familiar. Now, here's what I'm going to introduce to you. Technically, we actually say that water's ionization is actually in an equilibrium with itself, because that strong acid and strong base will then transfer the proton that it just transferred to go back to 2 water molecules. So what we see is actually an equilibrium within water's auto-ionization and auto-neutralization. And so what we do is we have a K value, a K equilibrium value for water that we symbolize as K sub W to represent, this is the equilibrium specific for water. And what we say is that at 25 degrees Celsius, because remember, temperature is the only thing that can change K value, that the ion product constant for water, or the water ionization constant, is 1.00 times 10 to the negative 14th. And that actually equals, okay, that equals the concentration of H3O plus times the concentration of OH minus per hour, okay, per hour, K equilibrium rules. We never count liquids either. We would say that a liquid would be 1, so we wouldn't technically count it in the K equilibrium expression, okay? So when we raise this to the log, pKW is equal to 14, and that is equal to POH plus pH. So you're seeing, oh, this is where we get these values from. This is where we start seeing the manipulations come into place with the conceptual understanding of equilibrium. So that being said, as you're starting to realize, one, KW or K equilibrium unit 7 is definitely not going away in this unit. But two, that helps us actually expand in our tool set of how to calculate for unknowns regarding pH and POH of an acid and base in equilibrium, and in water, especially when water is one of the reactants, okay? So I go back to up here, the sample problem, and I realized I should have moved that sample problem down. But what we have here is a 0.10 molar aqueous solution of aspirin at 25 degrees Celsius found to have a pH of 2.27, okay? And so determine the H3O plus and the OH minus and the POH for the solution. So I'm going to ask you to put a lot of things together. So first and foremost, you're told the pH. So from pH, you can get H3O plus concentration. So H3O plus from pH using one of the manipulations revealed up here, okay, is equal to 10 raised to the negative pH. So I say 10 raised to the negative 2.27, and that is a 2 sig fig pH value. So that means I'm going to have a value of 5.4 when I plug into the calculator times 10 to the negative 3 molarity. Okay, then for OH, okay, I know that the concentration of OH, all right, well, I'm actually going to use the idea that KW, which is always a known value, it's always 1.00 times 10 to the negative 14th, is equal to the concentration of H3O plus and OH minus, because I'm in aqueous solution. So I can say that I have OH minus is equal to, rearrange that equation and it becomes KW all over the concentration of H3O plus. Well, I know my H3O plus is the value I found above. And so I say that's equal to 1 times 10 to the negative 14th. And I know I'm not writing all my sig figs right now just because I'm trying to save room, of 5.4 times 10 to the negative 3 molarity. Okay, and I get that I have a value in molarity of 1.9 times 10 to the negative 12th molar. And again, I'm sticking to 2 sig figs, okay, because I'm limited by my H3O plus, which was limited by my pH measurement. Now, that's 2 out of the 3 that I need to determine. I need to determine the H3O plus. Boom, did that right there. I need to determine the OH minus, did that right there. And finally, I need to determine the POH. Well, obviously, if I now have OH, I can just plug in to the calculator that POH, okay, is equal to the negative log of my OH concentration. And that's going to be equal to the negative log base 10 of 1.9 times 10 to the negative 12. And that's going to equal 11.73 to the 2 sig figs, which are represented by the 2 digits after the decimal. And that means I have color coding. I have now found the POH. So this was just like a really fancy long problem where it shows you how you can use pH, POH, and KW to actually be able to, from any point of an acid base problem, whatever you're given, you can use all these relationships to solve for various unknowns. So it's really just at this point algebraic manipulation, knowing the necessary relationships. So sorry, that was a bit of a longer one. This unit is going to be a very math heavy unit. And I just want you guys to strap yourself in and prepare. It's going to be a lot of math, but I want you to be confident that there are patterns. You'll notice that a lot of the math mimics one another. Okay, so your really big focus is learning the process and the clues of how to identify in the prompt the context of each process. Okay, but yeah, good luck, everybody.